Okay, thank you very much for inviting me to give this talk. This is, I need to make a couple of disclaimers, but first, let me tell you who's not guilty. My co-authors, this is a joint work with Ed at the Bank of England, Jay, that is my remote PhD student at Columbia, and Katie Yuan from the LSE. I'm going to be talking about endogenous risk reaction in a financial network. What I've been doing all my life was asset pricing. This is going to be very different. And the reason being that as a profession, as financial economists, if you think we started early in this century or the middle of this century, we had models in which equilibrium processes were given by some unknown gods and we were choosing optimal policies. Then Bob Lucas told us, well, that doesn't really make sense. So we took that lesson and we started working with processes in which actually the drift was endogenous, the risk premium was endogenous, but the rest, the risk was still given by some unknown god. Then the recent financial crisis came about and we realized that maybe it's time to start understanding how risk comes about as an equilibrium quantity. Is what I'm going to be talking about today, and it's going to be based on network theory that is relatively recent. I'm going to show you that the framework we're going to be using is extremely simple, but not simplistic. So the idea behind is that a real effect in the economy can be generated by financial intermediation. In the old models, is odd for somebody born in the 70s calling models of the 70s old models, but in the old models, monetaristic, we were talking about financial intermediation as being creating inside money or liquidity in the network jargon. Nowadays we think and we learn that actually the role of intermediaries of creating inside money can generate aggregate risk. And that's exactly what is behind the rationale of the previous talk, those capital ratios and so on we talked about. The previous talk was talking about microprudential regulation. That is the idea of looking about individual agents' behavior and putting some normative behavior on them such that they become safe. What I'm going to be talking about is totally different, actually. The idea is that I don't care about individual agent behaviors unless they have an effect on the aggregate. That is, in a sense, is an extremely liberal view of economic regulation. In the sense, as long as you don't have equilibrium aggregate effect, I don't care about what you do. Okay, that's going to be the idea behind. And in this paper, we are going to be studying an interbank market of borrowing and lending in which liquidity is the liquidity that banks provide and hold is an endogenous variable, and actually in which each agent's choice is going to change other agent's choice. It's also going to change the aggregate risk for the system. Now, as I was saying, network theory applied to financial models with shocks actually is extremely recent. This implies that it's going to make some people smile, but outside the linear quadratic frameworks, we don't even have general existence of equilibrium results. So we're going to have a very simple framework. It's going to be a mean variance, linear quadratic. But once we do this pact with the devil, we are going to be able to identify the equilibrium amplification mechanism, the multiplier of shocks. And what is going to be important here is the standard, what I teach every other week in Finance 101 classes, the standard 1/n argument of diversification is not going to hold true. In a sense, this is the argument of Acemoglu econometric paper, the network origin of aggregated fluctuations. Once agents interact in a financial network, it's no more true that idiosyncratic shocks are going to wash away. Actually, we are going to have, every idiosyncratic shock is going to matter in the aggregate. And since we have the idiosyncratic shocks, individual agents do matter in the aggregate, we are going to be able actually to identify what we call liquidity level key players. We're going to be the ones that if they were to default tomorrow, they would generate the largest reduction in aggregate liquidity in the system. So if your type of economic policy is of the interventionist type, I'm not saying that it's mine, you would think those are the guys that you might want to bail out, conditional on a financial distress. But also we're going to be able to identify what we call, and I think this is one of the key novelty of the paper and one of the interesting elements, what we call the risky player. That is, those are the ones that are going to be agents whose individual shocks will have a largest effect in the aggregate. There is no need for default. Okay? And one thing that is going to be quite cute. I'm going to show you here that everything that we try to do in response to the recent crisis, tighten up the capital ratios and so on, is not going to help us at all. Actually, it's going to make us think that we are safer, but we are not. Nicely enough, we're going to be able to solve also, since it's a relatively simple game, also for the central planner problem. Why this is going to matter? Because when you have a game in which my actions depend on other people's actions and vice versa, what is going to happen typically there is an externality of my action on other people. If I'm playing a Nash equilibrium, I do my optimal choice. I'm not going to internalize the externality I generate. This implies that the Nash, the centralized equilibrium, and the central planning equilibrium are going to be different. We're going to be able to characterize that wedge. Now, we're going to have a structural model that actually we designed with the intent of making operational. So we are looking for a setting that we could use as a case study. And we, thanks to Ed, that is at the Bank of England, we had this fantastic market that is the UK payment system, the Interbank payment system. To give you an idea, this is a market that per day intermediates half the GDP, 700 billion a day. And this is a system, there are theoretical reasons behind which, in which the payments are not netted out. There is gross settlement. Okay? There is a reason why they do that. That maximizes profits. There is a paper that shows that. But it implies that since every player in the system has these random inflows and outflows, has to sit on a buffer stock holding or liquidity to smooth the shocks over time. Okay, I might receive a payment from Beatrice at 11, but I own a payment to Johannes at 1. If Beatrice is late, I need a buffer stock to cover that time short or liquidity. And to give you an idea of the exposures, this is a network in which there is a small set of banks, it's a dozen of banks, that are the core of this network. All other banks have to intermediate through this core. The typical peer-wise counterparty exposure is about 1 billion. Massive exposures, and for larger banks are about 3 billion. This is the type of network that if there is a collapse in this network, you don't get your cash out of the ATM. That's the type of market I'm talking about. Now, why a network might matter there? Well, the easiest idea is the one of domino effect contagion. You know, I'm going to use as an example. Beatrice, despite being Italian, she's a solid financial institution, but unfortunately, she lent me money. Okay, so this implies that, and I'm Italian too. So if I'm in distress, financial distress, I don't pay her back, despite her being a solid institution, I'm going to have a contagion effect on her. Okay, that's first generation models. An interesting type of mechanism that originated with Bhattacharya and Gale is the following. Imagine the story I was telling you. Each bank needs to hold a buffer stock saving on liquidity to smooth shocks over time. And think each bank is on an island. So you are banking on your own island and you are totally disconnected from the other banks. Okay, so you're going to choose in isolation your optimal buffer stock or liquidity. Then suppose that they throw bridges across those islands. So all of a sudden what happens is that if I receive a shock on my island, I can book the bridge and go to Beatrice's island and borrow some money from her to smooth my shock. If everybody does this, actually what is going to happen is that I'm going to strategically substitute my holding or liquidity with Beatrice's one. That is, I can reduce my buffer stocks because I can borrow from her. That was Bhattacharya and Gale idea. But it's not the only thing that can happen once I throw bridges, networks of contracts across institution. For example, me and Beatrice might compete for the same investment opportunity. Investment opportunity arises at random. We need cash to exercise those real options. If she's holding cash to exercise a new real option, I need to hold that cash if I want to compete with her. In that case, in the type of equilibrium, I get strategic complementarity. She holds more liquidity, I'm going to hold more liquidity. What our paper is going to have a model actually that nests those three channels. It's going to have a parameterization that, depending on the parameter values, you're going to get this different type of equilibria. And the reason being that we're going to be able to bring it to the data. Once we characterize the equilibrium, it's going to be quite easy. We're going to bring it to the data in structural form, and we're going to let the data speak about which type of equilibria we find in the market, what we find over time. Moreover, this is going to allow us to decompose the risk in the system into what is really exogenous risk and what is generated by agents' behavior. In particular, we are going to be able to construct what we call network impulse response functions. They're going to be like impulse response function in the time series dimension, but it's going to be instead across agents. I'm going to be clear in a second what I mean by that. So the model is going to be super simple. Remember, so I have those banks, each of them is on an island, and each of them has to choose their own level of buffer stock liquidity to hold, Li. Okay? And that's what, as later on in a couple of slides, as econometrician, I'm going to be able to observe. Now, here I'm going to play an intellectual fiction. I'm going to decompose this quantity, this buffer stock Li, into two quantities, okay, that are not observable, a latent, Qi and Zi. What is Qi? Qi is, the shuttle quantity, is the buffer stock saving that my bank I would be holding if it was not part of a network. It is on the island and there are no bridges across islands, okay? So, and if this was a function of coming out of an optimal linear quadratic model, I know exactly which form we would have. So I'm just imposing it. It's going to be a function of some fixed effect of the bank, some bank characteristics, some common factor in the column. Okay, that's what it would be in a mean variance world. So I'm putting it aside. The part where there is the action is this zeta. What is zeta? Zeta is the perturbation around the equilibrium holding that you would have without being the network because you are in the network. Okay, this is going to be where all the action is coming from. Okay, so I'm imposing this additively separability between the two. Now, how are we going to model this ZI? Well, I have to tell you how the network is going to work. So we are going to have a directed and weighted network. Why directed? Well, because me and Bea might be connected, but me borrowing from her or me lending to her are two very different activities. Direction of the flows matter, and me lending her $1, lending her $1 million is going to matter, so it's also weighted. Now, all the links on this network, this borrowing and lending network, this is fake actually, is going to be characterized by this matrix G, adjacency matrix. This is going to have as elements, the element Gij is going to be the fraction of I's borrowing that originated from J. That is, if you read it by rows, the adjacency matrix, it gives you basically the frequentist estimates of the probability of agent J lending to agent I. Okay, that's what it is. Very simple object. Hence, it's a right stochastic matrix. Large eigenvalue is equal to 1. What is going to be important in what I'm about to do, is going to be a shortcoming, nothing to say about that, is that at the time in which my player are going to be choosing their holding on liquidity, buffer stock holding on liquidity, G is going to be predetermined. The idea is you're going to take the network given, the connection of people you can potentially borrow and lend to, as given, and based on the connections, you are choosing your holding. Now, is this a great assumption? It depends. In a general model, it's not. If you think a model in which I were to sample data at a low frequency, that wouldn't be the case because you choose your network endogenously. We are going to be going at very high frequency in a small network that doesn't change much over time. So, as assumption, is not bad in our case. Now, we can generalize it, and there's the cheap trick that we haven't done it because, you know, in economics you have to let the referee ask you stuff to do. We can get exactly the same equilibrium if we split the game in two stages. That is, in the morning I choose G based on what I expect my optimal polyfunction to be in the evening, and in the evening choose liquidity. So we can do that in a standard trick. But for today it's going to be predetermined. One important thing is that when we bring this to the data, for everything I'm going to be telling you to be consistent estimates, I'm going to be fine even if G is not predetermined. As long as my best guess, my expectation, my physical expectation of G tomorrow is G today. Okay? And that would arise in the game, for example, split into two. So how is this so? Let's go back. Zi is the perturbation that comes from the network, and it comes because agents are in a network. How do you choose Zi? I anticipated you, it's going to be linear quadratic. So let's start from here. Now, what is the liquidity that bank I is going to have? Well, it's going to have its own holding, Zi, the cash that is putting under the mattress at the beginning of the day, plus the one that it might access, the one of the other agents, Zj, weighted by the links. What are the links? Gij is the fraction of I's borrowing coming from J. That is the frequency estimate of the probability that Zj is going to lend $1, weighted by some technological parameter. If Beatrice has $1, it's not sure that she's going to lend me the whole dollar, might lend me a fraction of that. So that's the accessible liquidity is going to matter. You know, first order term, second order term, linear quadratic. Now, the utility has only ordinary value, not cardinal value. Hence, we are going to scale it by we can scale it by the evaluation of this liquidity that is agent specific. We're going to introduce heterogeneity. And how we're going to model this valuation that is agent specific is the following. It's going to have a component that is just my own valuation, and potentially this coefficient might be 0, might depend on how much holding other agent can have. This can arise. Remember, I give you examples in which I care about strategic substitution. I can go and borrow from Bea, hence I value less holding my liquidity, or I want to compete for investment opportunity with Bea, hence I value more my holding liquidity when Bea holds that. In principle, this is not there. We're going to ask the data whether it's there. And why here we call it an information discount and so on? Because there is another way of microfounding this stuff. Based on non-Bayesian learning, is what Di Marzo and Vallanos do in a paper. They're exactly this type of form. The idea is that I learn from the people I interact with, I make contact with. That's the idea behind the percolation literal and so on. And this agent-specific component, has a non-random component plus as a shock. You know, I have shock to my valuation depending on what I expect to be my own investment opportunity or my inflows and outflow. And immediately you see that the marginal utility of agent I is affected by the action of agent J, depends really on the parameters delta, these haircut parameters, and this accessibility or leakage factor psi. So this, the way other agents influence my marginal utility might be either positive or negative. Okay, you can have both type of equilibrium. And equilibrium in this game, the unique interior equilibrium in this game is going to have optimal response function in which the choice of agent Zi is going to be a function of its own non-stochastic valuation, its own shock, and the choice of Z of all the other players, weighted by the links and this parameter phi. And this parameter phi is going to be key. It's going to be the key parameter in the whole talk. There is a convolution of the deep parameter I was telling you before, and has the following properties: that if phi is bigger than 0, when Bea is increasing her holding on liquidities, I'm going to increase my holding on liquidity. That is, we have an economy that is in a strategic complementarity equilibrium. While instead, if phi is smaller than 0, we have strategic substitution. That is, when Umut increases his holding on liquidity, I reduce my holding on liquidity because I can substitute internal liquidity and outside liquidity. Since the big matrix G is right stochastic, the conditions for equilibrium are trivial. For trivial equilibrium, just need this guy to be inside the unit circle. And the equilibrium actually looks like a mess, but it's going to be quite intuitive. The holding on liquidity of bank I is going to be this QI, the part that the bank would be holding if it was not part of the network, and the ith row of this matrix M, I'm going to come back in a second, times the valuations of all the banks. What is this matrix M? Well, this matrix M is just this infinite sum of which elements are quite intuitive. The first element is identity matrix. Thanks, unless I have cognitive dissonance, I'm connected with myself. The second element here is G, the matrix G. The matrix G is the matrix that contains all the first order links across banks. So those are all the paths of order 1s in my network. The second term is G square, that is all the second order paths and so on. That is, this M is a weighted sum of all the paths across players in the network. This matrix M takes into account all the direct and indirect links in my system. Now, once I characterize the equilibrium, I can characterize the total liquidity produced in the network, and obviously it's going to be a function of this matrix M. But the first thing that is interesting is that I can decompose the total liquidity produced in the network as a piece that is multiplying these average non-stochastic valuations and a piece that is multiplying the shocks, the heterogeneous shocks. And the first observation to make there is that what changes the equilibrium in this market, I already said, this parameter phi, both the first term and the second term are increasing in phi. A system with more strategic complementarity is going to have, on average, higher liquidity. That's what the regulators want. There is the desire since the last financial crisis. But the first thing that we point out is that, well, it's exactly the same term that is multiplying the shocks. It is very immediately a trade-off. You cannot have a system that mechanically produces more inside money, more inside liquidity, without increasing also the volatility of the system itself. Okay, it's exactly these two things go hand in hand. Moreover, we can use the equilibrium characterization of the total network produced liquidity by simply asking ourselves who's the riskiest guy in the system. Well, it's going to be the person whose shocks, VI, has the largest effect on the network produced liquidity. And it is once again just a function of this matrix M, of which we are taking the height column. Why is it so? Because the column spins down of the matrix M is how the system load on the agents. In network jargon, this is simply the out degree centrality of the agent. We can also ask who's the level key player. That is, who's the player in this market that if he or she were to be removed from the market would cause the largest reduction in aggregate liquidity. Well, yeah, this is just pinned down by, once again, the out degree centrality, but also this term here takes the rows of the matrix M. Why is it so? There is what is pinned down how, by participating in the network, I produce liquidity. Okay, so out degree, me affecting the system, level, both me affecting the system and the system affecting me. All quantifiable. Now, I'm not going to go to the detail of the equilibrium for the market central planner because it's just a mess, but I'm going to just give you the intuition why it's different, and then we're going to look quantitative why it's different. What a central planner would do, it would just take the individual payoff functions of buffer stock holdings and just optimize the sum of the stuff, and the optimality condition would be exactly the one that we had before, plus, remember here we had GIJ, that is agent I cares only how it's affected. We have all the term in GJI, that is all the externality that the agents is generating would be part of the equilibrium. In particular, it's going to start caring about how agent I affect other agents' valuations and holding, and how agent I affect the volatility of the liquidity the other players face because of my own action. It generates a wedge between the market central planner and market maker solution that we can characterize. Actually, I'm going to tell you in real time what was the difference between the two. So now I'm going to change my hat. I'm going to take my equilibrium. I'm going to take this equilibrium stuff here, and I'm just going to bring it to a data exactly in this form. Okay? Without making distribution assumption. I'm not going to need that. So the only thing I'm doing here is exactly the same thing I had. This is QI. I'm adding a T. I expanded it. And I'm writing what ZI is with a time subscript. And the shocks have any arbitrary distribution. The only restriction I'm having what I'm showing you today, that is, well, mean zero, obviously, but has constant volatility. In the paper, we also do it with time varying volatility, but the volatility of each agent is different. Now, if one stares to this stuff more than 60 seconds, if you remember that these are share of borrowing, so they sum up to 1, if you stare at it a second, you realize that if I give a unit shock equally spread across my n banks, the total effect is going to be 1 over 1 minus phi. That is, phi is spinning down an average network multiplier. And let me repeat it. If I give a $1 shock to my banks equally spread across them, the total effect is going to be 1 over 1 minus phi. This implies that when I'm in the strategic complementarity world, that is phi is above 1, the network is going to amplify shocks on average. When I'm in strategic substitution, phi is negative. Sorry, phi is below 0. Sorry, I said above 1, above 0, I should have said. When phi is negative, strategic substitution is going to dampen, it's going to reduce the effect of the shocks. Point 1. Point 2, Well, it's trivial from this equation to write down what is the variance of the total liquidity in the banking system. It's going to be a acute function of just this matrix M and the adjacency matrix at time t. What does that mean? It means that even if the fundamental shocks have constant volatility, even fundamental shocks volatility doesn't change over time, every time I change the nectar of contrast in the banking systems, the volatility of the banking system changes itself. Okay, any change in the network topology is going to change the volatility itself. So modeling it as constant is a bad idea. And last but not least, he said, well, can you estimate this stuff and identify parameters? I just have a run condition for this to happen. It's very simple. What is the condition that I have there? Basically, I need at least 2 players that don't have exactly the same actions in every state. Okay, that's all I need for identifying this stuff. Now, do I want to say this? Probably not. Now, so from the empirical model, I can identify impulse response function. Econometrics impulse response function are output, is the measured effect on the output variable caused by a shock. And that's exactly what I'm doing here is the network impulse response function of a shock of agent type on liquidity. It's going to be a function of this matrix M of all the links, of which I'm taking the column, is how the system loads all the action of one agent. And this implies that the network impulse response function, the agent that has the largest network impulse response function, is just the risky key player. It's going to be the most risky in the economy. Point 1. Point 2, this is a matrix that takes into account all the direct and indirect links. So, and last but not least, an impulse response function, many things are called in the profession impulse response function, but an impulse response function should be a decomposition of the variance. Okay? And that's exactly what these guys are. Network impulse response function, I vectorize them, I take the inner products, I get back my variance. So it's a way of decomposing the total variance in the system. Now, so we're going to bring this to the data. We are going to have intraday data. We're going to estimate a daily frequency. We're going to use intraday information to construct a lot of our controls. I'm going to use a strange data set, a strange sample between 2006 and 2010. Why I have those strange dates? Because it's the period in which there are no entry of exit from the market. It's a highly confidential data set. Entry and exit is public knowledge. If I were to use a longer data set, you would infer what we have. But it's actually quite exhaustive. Why is it so? Because it has roughly 3 equally sized periods in which one is the good times before the crisis, the other one is the crisis, then we have quantitative easing. And the network of banks are going to be all the members in this interbank payment system, the CHAPS payment system. To give you an idea how these guys are, that's what we have. That's basically, these are my guys. These are my banks. These are average over a week to avoid any inference from you guys in 1 second. Otherwise, the Bank of England will let me show it. So each flows are a borrowing and lending flow, average over the week. Thickness is the size. The size of those bolts are the gross borrowing. And what you have here actually is by bank the net borrowing. And one thing that if you stare a second here at the net borrowing is that as an economist, I always thought about the interbank market being a boring market in which, at the end of the day, if a bank has too much liquidity, it's going to lend it out. If a bank has too little liquidity, it's going to borrow. Okay? Well, this implies that you would expect the net borrowing for each bank to fluctuate one side or the other. I should stop it now, a second. Fluctuate one side or the other. But it's not at all what you find. Okay? If you paid attention to the video so far, you found that those banks are systematically one side of the market or the other. Okay? So it's not this random thing. The other thing I wanted you to observe is that when the crisis starts, right? If we look around, we read over and over in newspapers that when the crisis started, there was way less borrowing and lending, not in the interbank market. The overnight interbank market, actually, those lines are becoming much larger. Those arrows are becoming much larger. Okay? Why is it so? Because there was no other way of borrowing and lending across banks. And then let me fast forward to what I want to show you is that when quantitative easing comes about, when those banks start being able to borrow cheap from the central bank, my network is becoming anemic. Right? The video too, there is no action left. Arrows are thin, there is very little. So these are the history we look about. And our network proxy for the links is going to be the fraction of banks' loans borrowed from Bank J, and these are relatively stable network, actually. The largest eigenvalue of this guy is 1, obviously. So if you think what is the propagation, what is deriving the propagation in the second large eigenvalue, that is, until quantitative easing, is a quite stable quantity. So it's a relatively stable network. It implies the fact that we give it as predetermined is not such a bad assumption. And then, remember, well, that's come from the theory, but one has to be conservative when you look at the data always. And the way we are going to be identifying the network effect is basically as a latent unobservable variable. Okay? So I want to stack the cards against me finding any effect. This means I want to saturate, put as much stuff as possible as explanatory or liquidity holding. Now, that's exactly what we did in the following approach, is that we survey the literature of about looking for everything somebody had proposed should explain liquidity holding for the banks, and we put it inside. That's really the kitchen sink approach. So we are stacking a card against us finding any effect. And a lot of this stuff are not observable to the general public. For example, how much those banks strategically delays or anticipate payments and so on. But we could because we have supervisory data. So that's the kitchen sink. Now, this being the data, we are going to split our data into roughly 3 subsamples. The good times, the pre-hedge funds crisis Northern Rock bank run, the financial crisis that is from the Northern Rock bank run to the announcements of the British QE, and then we are going to have the last part is going to be the British QE. Now, one thing I'm going to anticipate is that, remember, the key of the type of equilibrium and what happened to a shock in the system is about all this parameter phi. There is a convolution on the parameters. What we found is that actually this estimate of phi is going to be very different. So we are going to do next, in a few slides, we are going to allow this phi parameter to be estimated in a rolling fashion to move over time. Okay? So let me show you the sub-period estimate. So period 1, good time, financial crisis, quantitative easing. This coefficient is always highly significant, despite the fact that they saturated these regressions like crazy, and is largely positive in the first period, still positive in the second, and then negative in the third. That is, strategy complementarity, much less strategy substitution. Now remember, I was telling you that the average network multiplier, it would be simply 1 over 1 minus phi. The average effect of a shock equally spread across the network. Well, this phi of 0.8 implies basically an average network multiplier of 5. That is, I give I should say pounds actually, I always get it wrong. I give a 1 pound shock to this system. The total, to the banks in the system, the total effect would be about 5 pounds. It looks like an enormous multiplication here. Now, you might say these are huge numbers, right? Well, I can go even further because I can decompose this amplification of the shocks into the contribution of each bank, what I was calling before the network impulse response function. What I'm plotting here. Here, the index here are the various banks in the system, and here is the network impulse response of a unit shock in deviation from the shock. What does it mean? This number here, for example, 14, this means that if I were to give a $1 shock to this bank, bank 5, this would become, for the system, as a shock of 1 plus 14. That is, if you look at those pictures, each of these banks, you realize that, yes, there is a massive network multiplication, about 5 is the network multiplier, but all the risk is generated by 1, 2, 3, and maybe 4 banks. Well, it's very funny, actually, we get 4, because if you look at old economic history books, 1900, 1800, the British banking system used to be referred to as the system of the Big Four. We still get just 4. But the names are not, I cannot say anything on the names, but not what you would expect sometimes. So, massive multiplication by this force. But you might say, okay, this is before the crisis, right? We have seen that probably we should be able to spot these guys, and now these guys are well regulated, right? We will look at capital ratios. Now, how would a flag would be raised for any of those banks? Very easy. If these guys are borrowing a lot relatively to their capitals, they're going to pop out in the capital ratios. So, remember, 4, 5. Well, let's look at their borrowing. Is it 4 and 5? No, 5 and 9. Sorry, I can't count. That's what economists have as a problem. So 5 and 9. So 9, yes, is a net borrower. Capital ratio will spot this one. Bank 5 is a net lender. There is no way expected shortfall, value at risk. You wouldn't spot this guy. Now you might scratch your head and say, what is going on? Well, I was telling you before when I was showing you this Star Wars movie, that my prior, the interbank market being very boring, was totally wrong. I was thinking about a market in which actually if I have excess liquidity, I lend it. If I don't have enough liquidity, I borrow. It's not how it works at all. Suppose I have a marginally better, we are talking about basis point, credit standing than Beatrice. What I'm going to do, I'm going to come to you guys, borrow, to be able to lend to her. I multiply this by exposure of 3 billion a day, I make a profit. That is, you might generate tons of systemic risk, like bank 5, bank 6, even by being a net lender. Something that Basel 2, 3, and so all the ideas in regulation so far would never spot. And you can see it only if you look actually back at my Star Wars picture. Is that bank 5 is borrowing a bit, quite a bit, is the third largest borrower, but is a net lender, but is borrowing a lot because he's lending a lot to people that are very risky. It's the network or contract that is pinning down risk in the system. You wouldn't see it with any of the regulatory system put in place so far. Now, this was based on period 1. In period 2, we have still a positive 5 hence net amplification of the shock on average 1.4. And if I look how the network impulse response function look like in these periods, are much dampened, but still most of the amplification comes from a small subset of players. Okay? And what is interesting here is that the network amplification here is smaller, despite the fact, what I showed you before in the movie, but we have tables in the paper, the amount of borrowing and lending actually during the crisis period is higher. And why there is lower amplification is exactly the type of equilibrium, the equilibrium phi to which the system is gone to. And the one that is pretty telling about the last period we have a negative phi. This implies that shocks get dampened. A unit shock becomes less than a unit shock, or if you want, liquidity injection, a $1 injected in the system via quantitative easing becomes less than $1 by a factor phi. You can see that most of this absorption of shocks actually is generated by a few banks that are playing the strategy substitution, if you want, the free riding equilibrium. And interestingly, those are the same players. Now, this table gives you a stark contrast of phi in the various regimes. So I would like now to show you how this phi evolved over time. And so what we do, we can do it simply, we have high frequency data, so we have no problem doing this. We can estimate phi over a rolling window. And remember, phi positive, amplification of shock, phi negative, dampening of the shocks. We do this with a 6 months window. Here we have a first phi starts very positive. We have a first jump here. This comes from the fact that the ones among us that are US educated, I should have made this clear from the beginning. In the US, bank holdings are not a decision variable. There is a regulation, the Federal Reserve decide your minimum reserve holding. In the UK, those are a pure decision variable. Now, what has happened here is that this change is basically when the Bank of England, and this has been removed during the crisis and since then, asked the banks to just report what their target holding would be. And they have to report it over the next 3 months, and there was some penalty if they were to fail to achieve this target. And what you see is that before the hedge fund crisis, substantially higher positive phi. As soon as the hedge fund crisis hits, actually, we move to an equilibrium in which phi is very close to zero, very small amplification. If you want it, it's not what I was expecting. I went to Princeton, but this is a beautiful neoclassical reaction. That is, the system moves to an equilibrium. The natural equilibrium becomes is one in which there is very little amplification of the shocks. But after the hedge fund crisis, actually the system is back to business, good as usual. Bear Stearns goes down way before Lehman goes down, but from Bear Stearns going down onward, there is no network amplification. This coefficient being zero all along and being zero even when Lehman goes down implies that in that period and going forward, a $1 shock to the system stay a $1 shock to the system. What does it mean? Well, for me personally, this means something very embarrassing. What I mean by that? This is the period in which the US started doing quantitative easing, around here, right after. And a set of economists in the UK were worried because Marvin King was the chairman of the Bank of England, was not doing the same thing here in the UK. And since the state of the economy tends to meet each other in the senior common room at the LSE, we decided to write an open letter saying, you know, the UK should do the same thing because we have a fear of a domino effect. That is, we let one of those banks go down, there's going to be an amplification through a network, big amplification. There was nothing on that. Here, the equilibrium is beautifully neoclassical. If you had let any of those banks fail, it would, 1 billion loss would be a 1 billion loss for the system. So no spillover. And then what happened here? Well, here is quantitative easing, but you see that our estimated phi start moving to the negative region actually before getting to the quantitative easing. Well, I was giving you a background on the size of this market. It's a market intermediate 700 billions per day. By the end of our sample, the injection of liquidity by the Bank of England in this market was 275 billion. So a huge injection. At a scale is a third of the market. Well, what you find here, negative phi means that agents are free riding on aggregated liquidity. That is, you increase your holding of liquidity, I can reduce my one, because if I need liquidity, I come from you guys. And exactly what we had here as a reaction. Our average point estimate is 1.8. This means that for every dollar that we pound, once again, that we injected in the system, we got actually an increase of liquidity of about 0.8 cents. Let me skip this one. And this is telling. This is, I will show you this change. You might think, is this change coming from the topology of the network, the geometry of the phi? Here I do the decomposition of the network impulse response function between first and second period and second and third period into what comes from G, basically who's in contact with who, and phi, the type of equilibrium. What we find is most of the action comes from the green line, the perturbation in phi. It's really the type of equilibrium this bank plays that changes. But the thing that I want to point out is that I glossed over is that we estimated a model in which we estimated a structural model, and we estimated a structural model of Nash equilibrium, that is, decentralized economy. But we solve also the central planner problem. There is a function of the same parameter. So what we could do, and what I'm about to describe, we could take our estimates of the D parameters in the decentralized economy and compute what would be the equilibrium values, volatility of liquidity and level of liquidity, in the central planner optimal solution. Basically, I can tell you what is the difference between the market equilibrium and the welfare maximizing equilibrium. And what I'm showing you here. And I'm showing you only two quantities. The first one is the difference in volatility of liquidity that you would have in the market equilibrium vis-a-vis what the central planner would like. And what you find is that right before the crisis, this market was already way too risky. Just using what we estimated in this period, so no crisis occurring, no distress yet, the central planner would have liked a 90%, a one-tenth of volatility of what it was in the market. But this, remember, I was telling you, you cannot have a market that produces a lot of liquidity without having a lot of volatility. For achieving such a basically one order of magnitude reduction in volatility, the central bank would be even willing to lose some of the level of volatility. Okay? Less inside money, less intermediation, much lower level of risk. Okay? That would be the optimal solution. The period 2, well, that's the financial crisis, the worst period. Still the volatility is very high in the system. The central planning solution would imply a much lower volatility, about 64% lower. But what we see comparing the market solution and the central planning preferred, that even though those banks are borrowing and lending more from each other, I was telling you, in this market there is more activity because there is nowhere else to lend. Nevertheless, the level of liquidity is too low relatively to the social optimum. So the crisis have, here you just have too high volatility, here you have too high volatility and not enough liquidity. The last period, the quantitative easing period, is the period that in my movie action was fading out, borrowing and lending was at zero, very, very thin arrow. Well, that's what comparing the market solution and central planning solution tells you that, well, in that period, the market is too boring. There is not much financial intermediation, there should be more volatility or liquidity. And the buffer stock saving of liquidity, the amount of cash those banks are sitting on, instead of lending it out, is too high. And it's actually a cute number because 27.5, right? The units here are 10 billions. Quantitative easing injection was 275 billions. Exactly the same number. Now, I'm gonna skip the literature because I'm gonna be on time. So what we have done, we had an implementable approach to assess interbank network risk with a deal with the devil, with a linear quadratic, super simple model. This allows us to identify the shock multiplier, identify risk level and level key players identification. This can be done in practice. Central banks can do this in real time. We have 3 central banks and a half. I cannot say the name, they are running this in real time right now. We can use those real-time estimations to estimate network impulse response function and see how shocks to the system shocks to individual would affect the system. And what we find is that we are the first ever to estimate this. We find a significant shock propagation mechanism for liquidity coming from network. And what we find is that this propagation varies significantly over time, can be very large, and there is no way to spot it with the traditional microprudential approaches. Implies complementarity and high risk before the crisis. It is kind of intuitive, actually, because if you think what this model means, what this phi is doing, is think about the first thing we have seen today, the CAPM in which you choose endogenously what is your beta with the market. In good time, you want a very large beta, positive beta, you want positive co-movement. In bad time, you want a negative beta. Okay, that's exactly why the equilibrium changes. And that's exactly why we find basically zero in reaction to the Bear Stearns crash, totally rational reactions, and we find evidence of free riding on aggregate liquidity provided by quantitative easing. And interestingly, we find that most of the systemic risk, at least in the UK market, is generated by a very small subset of key players. And I'm done, bang on time.
Nice. Other questions? Comments?
You might have said, but I probably missed it. How do you differentiate the key players from the others in the model? Like, I My question is basically like if you probably it doesn't make sense in the short run, but if it goes to like the long run, then you move from being one class to another class.
You're gonna the nature of that is gonna change over time. At every point in time. Now, the important is that I lost it. This is a function whose which type of equilibrium is a function both the network topology and the type of equilibrium. It implies that this changing over time is going to change who's the relevant guy. And phi, in principle, if this quantity were to jump around, you think that this is a multiple equilibrium model. Different phis are multiple equilibrium. If this phi were to wildly jump, today is U, tomorrow is bear, and so. What you find in empirical, those are very stable actually. Okay, and most of the change or risk comes from phi, not from G. But in principle, it might change from one day to the other.
In your analysis, you fix the G and have you.
It changes every day.
It changes.
Changes every day. We don't fix it.
How does the welfare depends on the structure of the G?
Well, okay, I have it on the paper. I don't have it on the slides, but the central point solution looks exactly the same with a m that is different. There is a function of the other parameters. You take this one, you plug into the sum of the utility, gives me my welfare. We haven't computed that, but we just have computed equilibrium quantities. Now, what you have is that you get a trade-off, is that there is an optimal connectivity level. That is, if I make a very connected network, condition on a positive phi, because negative, the other argument applies, a very connected network, high average clustering coefficient, you're going to produce a lot of liquidity on average, but you're going to produce optimal volatility. But you're going to produce high volatility. So there is the complete network is not the social optimum. Okay? But if phi is negative, you have the other way around. So there is an optimal level of connectivity. We didn't compute it, but we could actually.
Other questions?
In the third period, do you want to add the central banks and add another nodes?
The central bank is another node. The central bank is, among the controls, is what the central bank does. I cannot show you anything about the central bank, though. But it's there. It's in our estimation, yes. The quantitative easing injection is there, but it's not in my movie and so on.
Other comments? If not, we can hold the speakers of the
Thanks a lot.
again.